Most people think metamaterials and compliant mechanisms are exotic research topics with no real-world use. But the truth is much more practical. They exist because traditional rigid parts and conventional materials have reached their performance limits. Engineers are no longer asking only what material to use. They're asking how geometry itself can create new behavior. To see this clearly, imagine a simple everyday situation where you squeeze a foam stress ball. It deforms smoothly, stores energy, and returns to its original shape without hinges, joints, or separate moving parts. Without realizing it, you've interacted with the core idea behind compliant mechanisms. Motion created through controlled flexibility, not rigid joints. What's actually happening here is simple. Metamaterials get their properties from structure rather than composition, and compliant mechanisms achieve motion through elastic deformation. By carefully designing geometry at micro or macro scales, engineers can create materials that bend, twist, absorb energy, or respond in ways conventional materials never could, all while reducing parts, friction, and failure points. Now imagine a real engineering scenario, designing a lightweight drone landing gear. Traditional designs use multiple rigid parts, joints, springs, and fasteners, all potential failure points. With compliant mechanisms, the landing gear is designed as a single continuous structure that flexes on impact, absorbs energy, and returns to shape. Using metamaterial-inspired lattice structures, stiffness is high where strength is needed and low where flexibility is required. FEA validates deformation limits, and AI-driven optimization fine-tunes geometry. The result is fewer parts, lower weight, no lubrication, and dramatically improved reliability. This isn't futuristic. It's already happening in aerospace, medical devices, and robotics. This same logic is spreading across industries. Metamaterials enable vibration isolation and impact absorption. Compliant mechanisms power soft robotics, medical implants adapt to the body, and wearable devices become lighter and safer. Engineers are no longer forced to choose between strength and flexibility. Geometry delivers both. The scientific foundation of compliant mechanisms was advanced by researchers like Larry Howell, who demonstrated that motion and force transmission could be achieved reliably through elastic deformation rather than rigid assemblies. His work shifted mechanical design from assemblies of parts to behavior encoded in shape. In practice, future-focused mechanical design follows a clear workflow. Design intent, geometric architecture, material behavior, simulation and optimization, manufacturing validation. The engineer doesn't lose control. They gain a new design language where shape becomes function. Now that you understand metamaterials and compliant mechanisms, you've reached the frontier of mechanical engineering, where materials, geometry, simulation, and AI converge. This is not the end of mechanical engineering fundamentals. This is what they were building toward all along.